Okay, good evening, gentlemen. Na karibuni. This evening we want to look at this topic called route control. How to control traffic within our network. So I'll read the forward. Enterprise networks may encounter problems such as unauthorized access of certain traffic, and the other problem is suboptimal traffic path selection. Now, to ensure data access security and improve link bandwidth usage. So two things, security and improve link bandwidth usage. Traffic behavior on the network must be controlled. For example, so especially when we don't want certain people to access certain resources in our network, we can do reachability control. To ensure that some links don't stay idle in our network, we can do traffic path adjustment. So we have tools. Tools may be required to meet complicated and precise traffic control requirements. So this course introduces the traffic control tools and their usage scenarios. By the end of this chapter, you should be able to, Eric.
Number 1, master the method to control network traffic reachability. Number 2, master the method to adjust network traffic paths.
Yes.
Number 3, be familiar with the problems caused by route important solutions.
Okay, wonderful. Thank you. So we want to begin with the traffic behavior control requirements. Then later on, we're going to look at how to control reachability, how to adjust the network traffic path, and also we're going to look at problems that might result from doing route import and solutions in our network. So we have two requirements, traffic behavior control requirements that we might want to implement in our networks. The first one is to control traffic reachability, and the second one is to adjust the network traffic path. Now, it is important that you remember this particular scenario because it's what we are going to be using in most part of this particular topic. Now, for example, your network is made up of 4 routers. They're sharing routes using OSPF. Then you have the marketing department, you have the HQ, and now you want the marketing department not to be able to access the finance department. So you don't want the traffic from the marketing department to be able to access the finance department. Similarly, you don't want the marketing department to access R&D department. You don't want the headquarters to access the R&D department. But all of them can maybe access the documentation department. So this, most of the time, is done in order to enhance network security. So that particular traffic behavior control requirement is what we're calling controlling reachability, traffic reachability. So what can be accessed and what cannot be accessed and by who? Control traffic reachability. So we are going to see clearly how that is done. And the second bit now is on adjusting the network traffic path. So the marketing department can access the headquarters via this route or this route. So the reason as to why this route is not being used is because we are using OSPF between these routers. And OSPF is going to compare the link cost. So this one has 5 Mbps, for example, this one has 10 Mbps. So generally, this packet is always going to be forwarded through this route and not this route because of the cost. Now, when that happens, 2 problems might occur. The first problem is that this link might be overwhelmed, and therefore congestion might occur, which might cause packet loss. That's problem number 1. Problem number 2 is that this link will remain idle. So it will never be used unless we now do some network traffic path adjustment. So generally in this topic, we are going to look at different tools that you can use to achieve this. Different tools that you can use to either control traffic reachability or adjust the network traffic path. So let's begin with controlling reachability. To control reachability, you can use one of 2 options, what we call routing policy or traffic filter. Traffic policy or routing filter. So we are going to look into each one of them and how they're implemented. So the scenario is what I had explained earlier, that we want to make sure that the marketing department cannot access the finance department and the R&D department. But we want to make sure that the headquarters cannot access just this. The HQ cannot access the R&D, but maybe all of them can access the documentation department. Now, as I've said, to do traffic control reachability, you can use one of 2 methods. The first one is what we are calling routing policy. And the second one is what you're calling traffic filter. So what's the difference between these 2 methods? Now, this one is used to change the number of routing entries to control reachability. That is to filter. You filter received and advertised routes. So you filter the received and advertised routes. Remember, for RTC to be able to send a packet to this guy, RTC must be aware of this network. How? It's going to be aware of that network through OSPF. Because these routers are sharing their networks through OSPF. But using a routing policy, we can actually filter. We can actually filter this network so that RTA maybe does not share it into OSPF, or we can simply configure RTC so that RTC does not learn about this network. So that is what we call a routing policy. So we can configure that. Okay, so let's also look at this. So what about traffic filter? Now with traffic filter, it's used to either deny or permit specified traffic flow. Deny or permit. Deny or permit specified traffic flow. So generally, if we're having a packet from the marketing department, it will have the source IP address. So we can simply configure in RTA that, hey, if you get a packet with this source address and the destination address is the finance department, just drop that packet. Drop that packet. So you see, with traffic filter, we are not really affecting the routing entries. We're not affecting what goes into the routing table. We are simply denying or permitting a specified traffic flow. So these are the two ways in which we can be able to control traffic reachability in our network. Now, generally, with the routing policy, you want to achieve a number of things. So these are some of the things that a routing policy can enable you to achieve. Number one is to control route advertisement. So what route are you allowed to advertise? Number two, so we're going to do most of these things. You can also control route receiving. So which route can you learn about? Then you can also filter and control imported routes. So remember, imported routes are routes that you're learning from other protocols. So that's the other thing that you can achieve. And you can also actually set route attributes. So, you can set route attributes so that you can affect, for example, reachability. So remember, we looked at BGP attributes. So those are some of the things that we are going to learn about: how to control advertisement, how to control route receiving, to filter and also control imported routes in this particular scenario. So let's look at that. Okay. Wait, this, okay. So the first solution to control reachability is route policy. So we've seen that we can either do a filter policy, the filter policy tool to filter the routes that are imported. So route policy has a filter policy tool and a route policy tool. So filter policy tool used to filter the routes imported from RTA into the OSPF. So we want to control what RTA, the routes that RTA will import into this OSPF arena, because OSPF is between these interfaces. So we can decide if these interfaces are not participating in OSPF, then what can we be able to import into OSPF? So a filter policy will help us to do that. And also routes that are imported from RTC to the routing table. Routes imported from RTC to the routing table. So what is it able to learn from OSPF? So we can also do that using a filter policy. When you're using a filter policy, most of the time we simply use an access control list or an IP prefix list to match the target flow. So we are looking at a certain address and maybe mask like that. Then after that, we now use the filter policy in the protocol view. So for example, in OSPF1, to advertise policies for the target flow. So we're also going to do that right now. Okay, then route policy tool is used to filter direct routes that are imported by RTA. So simply direct routes. Again, when you're using a route policy, we can either use SEL or IP prefix. Then after that, we use the route policy in the protocol view, to control the imported routes. Now, generally, some of the common filters that are used, other than those two that we've looked at, let me see if I can get rid of this. Okay. So some of the filters that are used to filter traffic flow include access control lists. We also have what we call prefix lists. So we are going to look at that. You can also use attributes such as the ASPath filter. You can also use the community attribute filter. You can also use extended community attributes. And there's also another one called the RD filter. So these are some of the filters. In this particular topic, we are going to look at SEL and prefix. So this is access control list and prefix lists. Okay. So access control lists are normally used. Access control lists classify packets into different types based on the packet information. So as we know so far, SELs are simply used to identify traffic flow based on a number of parameters. Depending on the type of SEL. We know that types of SELs. We know that, for example, we have basic SEL that is created using a value between 200 all the way to 2999. And this one simply uses the source IP address to identify a traffic flow. Then we know that we also have the advanced SEL, which uses a value between 3000 all the way to 399. And this one now uses a number of parameters other than source, so source and destination. Destination IP address, also the layer 4 transport layer parameters. So it can also use layer 4 parameters and so on and so forth. Then other than that, we also have at number 3, we have what we call the layer 2 SELs, which uses the MAC address, uses a number, of course, between 4000 all the way to 499, and this one is based on MAC address. Then we have another one, which is called a user-defined, the last one, user-defined SEL. User-defined SEL is created using an ID that has a value between 5000 to 599. Now, user-defined SEL matches packets against user-defined rules. So this one is against user-defined rules. So it can also use a combination of parameters, just like advanced SELs. Now, as we know, SELs will match rules rule by rule. Each rule has a number which uniquely defines the rule. So for example, here we are creating a basic SEL. So SEL 2001. So each rule will have a unique identifier. It's called the rule ID. And therefore, rules are evaluated in ascending order of the rule ID. So from rule 0 to rule 5 to rule 10 to rule 15. Why am I jumping 1, 2, 3, 4? Because rules are created, created using an interval of 5 for better management. So for example, here we're saying rule 0, then permit source. Permit source, then we put, for example, the network address of the address that we want to permit, and we do a reverse mask, and this reverse mask is what determines what should remain the same and what should match exactly. So anywhere we have zeros, that part should remain the same. Otherwise, anywhere we have ones, then this part can vary. So any packet that is coming with a source 1.1 dot anything else will be permitted with this SEL. So for example, if we can look at this example here, which packets from this rule, which networks here can be allowed to pass through? Can anyone give it a try? Anyone? If we have these networks, 1.1.1/32,
the third one.
This one. Which one?
The
third one, eh?
The third one. With 1.1.0.0/16.
What about this one? What about the second one?
Yeah, the third one.
The second one, will it be allowed?
I think also the second one. A and D won't be permitted.
Okay, so I just wanted to let you know. Some time back, I used to think that actually this is the inverse mask, but it's not necessarily true. What this determines is what must match. So for example here, these two octets, these two parts must match. So you have to know what will be allowed, just ignore the mask completely. Don't look at the mask. Just look at the 2 zeros, then look at that and look at these 2. So anything that has these 2 will be allowed from this particular rule. So actually, if you look at that, then what will not be allowed by that rule is actually this guy here. So SELs do not really take into account the mask. So I hope you've understood that. Now, what happens with SELs? We must have learned this during HCIA. What happens when a packet does not match any rule? When a packet does not match any rule, what happens to that packet? Is it going to be dropped or is it going to be forwarded? If a packet does not match any rule, is the packet going to be dropped or is it going to be forwarded? Anyone? Alan, what is your guess? Marvin?
Forwarded.
Exactly. So with SELs, any packet that does not match any rule, we look at rule 0. If it does not match rule 0, we go to the next rule. If it does not match the next rule, we go to the next one, up to the last one. If it does not match any rule, it's going to be forwarded. So it's important that we remember that. But what if it matches a rule that has a deny? So at this particular point, we can either have a permit or a deny. So what if we match a rule that is deny? What happens to that packet? Hello, can I be heard?
Yes.
Okay, so what if we meet a packet that has a deny?
It won't be forwarded.
The packet is
discarded.
Exactly, the packet is discarded. Okay, so here we're just showing you the networks that this rule is actually going to allow. Okay, so let's go on and look at another example here. So here we have a basic SEL again. So rule 0, permit source. So we are permitting that, and we are putting all zeros. If we just put a single 0, it means all zeros. So this rule number 0 here, or which network is it going to allow here? The very first one here, right? Because it's a permit, Cindy.
Yes.
Okay, let's go to rule number 1. Now, it's not compulsory for you to name rules with the interval of 5, but it's recommended for easier management. So that when you add rules without specifying the rule ID, the system will automatically create for you by incrementing the last rule with a value of 5. Okay, so this one, rule 1, deny source. So this one. So which one is it? Which one are we barring here? This one will capture this one, right? That one. Then rule 2, permit source. Rule 2, permit source. So here, you have to check these 2 zeros. So these 2 parts have to be the same. These 2 parts have to be the same. And this one also has to remain constant, but now this one can vary. This one can vary like that. So that one will, I think, allow this one here. Then it is recommended that the very last rule, the very last SEL rule that you specify has a deny clause. So rule 3, deny source any. So that if a packet does not match any rule, then it's simply dropped. So you can have either deny or permit source any. Actually, it's recommended that you set it as permit source any, so that any other thing that is not denied, it's allowed, any other packet. Okay. So from that, we can see that from this rule, the 2 that have been permitted are 1.1.1/32 and 1.1/16. I hope we remember that. Okay, so what else do we have here? I think this is another example This is another example of an ACL. So we have rule 0 permit source 1.1.1.0, then 0.0.0.0. So if this is packet number 1, number 2, number 3, number 4, number 5, which packet is this rule going to permit? Number 1, number 2, number 3, number 4, or number 5? Which one is it going to permit?
This is just a guess, but 2, 3.
Yes?
Will it permit 2 and 3?
Exactly. That is very true. It's going to permit 2 and 3 because we've said that ACLs do not consider the mask. ACLs do not consider the mask. So let's look at this. So indeed, it's 2 and 3 that are going to be allowed. But now, what happens? What happens if we want to filter out the route 1.1.1.0/25? So how can we do that? So ACL can flexibly match packets against IP address prefixes, but cannot match the mask length. So that's the biggest undoing of access control lists. Now to cater for that, we have what we call IP prefix. IP prefix. IP prefix list. Now, generally, an IP prefix list can match both the IP address prefix, and the mask length. IP prefix cannot filter packets, IP packets. They are only used for filtering routing information. They are only used for filtering routing information. So while ACLs filter IP packets, IP prefixes are used to filter routing information. So when you talk of IP packets, we are talking of data flow. Data that is flowing is filtered. So ACLs are used to filter data that is passing through the router. But IP prefix are used to filter routing information. Which networks can a router learn about? So that is what IP prefix is used for. So here we have an example of an IP prefix. So IP, then IP prefix, then you give it a name. So here our name is test. Now, the other thing that an IP prefix must have is an index. So for example, index 10. While ACLs have an interval, a default interval of 5, IP prefix have an interval of 10. And IP prefix are important because the IP prefix are actually processed in ascending order of this index. So it will look at index 10, then index 20, then index 30, then index 40, and so on and so forth. The other thing that can follow is now a permit or deny. A permit or deny clause. Then the next thing that will follow is now what they call the IP prefix, which is actually the network address and the mask. Now, an IP prefix can also include greater or equal to, or less or equal to. greater or equal to, or less or equal to parameters. These parameters are simply used to specify a mask range. They're used to specify a mask range. So let's begin here. What this means /16 is this, that the IP range is that. So simply means that these first two parts must match, the others can vary, like that. Then what greater or equal to 24 means, and what less or equal 28 means, is this, that whatever comes with this address between this all the way to that can have a mask of 24, 25, 27, 28. So it can be /24 Donald, your camera is on. So it can be /24, 25, 26, 27, 28. So only addresses between this range that have this mask can be permitted. So that is what we call an IP prefix. So examples of networks that will be allowed with this configuration of an IP prefix. So these are just examples. So the first two parts must be the same, 10.0. So that is what /16 means, the first 16 bits. Then now, after that, the next thing is they can be /24, /25, or /26. So generally, that is the basic about IP prefixes. As I've said, the IP prefix index IP prefixes are processed in ascending order of the index, one after the other. If a deny clause is matched, then that particular network is dropped. If a permit clause is met, then that network can be learned. Now, if no IP prefix is matched, the default matching mode of the last IP prefix is deny. So unlike ACLs, where if a match is not found, we permit, we forward. Here, if a match is not found in IP prefixes, then we deny. So I hope that is clear. So we move on, and for example, look at this example here. So we have IP prefix pref1. So pref1 here is the name of our IP prefix, index 10. So that's the ID of this particular prefix. Then we're having a permit clause. Then we are permitting this. So 24, meaning the first three must match. Then we are specifying that the mask can be greater than or equal to 24 or less than or equal to 24. So that means we can only have a /24. So what this means, greater equal 24, less equal 24, means that we can only have a /24. So generally, what this means is that the only network here that is going to be permitted is this one here that has a /24. So please understand how we are doing it, because in the exam you're going to get such like questions. You're going to get such like questions. So understand how we are processing it, and if you have a question, please feel free to ask. So you see, while an ACL could not filter out this, could not filter out just this one. With an IP prefix, we can be able to specify the mask using the greater, equal, and less equal command. So I hope you've seen the difference between an IP prefix and an ACL. Now, these are just filters, but now the specific tools that apply these filters, one of them is what we call the filter policy. The filter policy tool. Now, a filter policy tool can filter the received or advertised routes. Received or advertised routes by ISIS, OSPF, and BGP. And BGP. So generally, remember with the filter policy here, we just want to specify which routes can be learnt and which routes can be shared. So when we are configuring a filter policy on a route that we want to allow to be learnt, we use the import parameter at the very end. When we want to filter which routes we can advertise in a particular protocol like ISIS, we use the export parameter. So how to do a filter policy? You simply write filter-policy, then you specify an ACL number. So for example, 2001. Or you specify an IP prefix, then IP prefix name. So for example, pref1, then import. So that policy will simply look in that ACL, do we have a permit or deny clause? So if we have a deny clause, then we cannot learn, we cannot receive that route. If in the ACL we have a permit, then we can learn that route. Similarly, if we have a permit in the IP prefix, then we can learn that route. If we have a deny, we cannot learn it. Here, we are doing the same thing. We're doing the same thing, only that now we are doing it in the export direction. Export meaning we are the ones that are supposed to advertise it. So if that network has a permit clause in either the ACL or the IP prefix, then we can advertise it. If it has a deny clause, then it means we cannot advertise it. Okay, so I hope that is clear. We go on and look at, so other than the filter policy, the other policy that we can use is what we call the routing policy. The route policy, sorry, route policy. So route policy is a powerful tool. It can be used together with other tools such as ACLs, IP prefix list, AS path filter. So it can be used with all the other filters. Now, a route policy consists of multiple nodes which have the OR relationship. Each node has multiple if, match, and apply clauses. Now, the if match clauses have an AND relationship. Okay, so let's see how a route policy is formatted. So you have to enter the value, the keywords, route-policy, then you give it a name. Then you use either a permit or deny clause. Then you enter the keyword node. Then you specify a number for the node. The node here is just like the index in SCLs and IP prefix. So you give it a number to uniquely identify it. So that's what we're saying, that it can contain multiple nodes. So a route policy can have multiple nodes. So you can have node 1, node 2, node 3, node 4, each of which has an OR relationship. OR meaning any node that matches is applied, OR. So this one or this one or this one, like that. Now, in each routing policy, in each node, on each node, we have multiple if match. So if this matches, then do this. So we can have another if this matches, then do this. So most of the time, under the if match, we specify an SCL or a next hop or an IP prefix. So if it matches this IP prefix, if it matches this SCL, then apply this. So apply means you can change the cost for that network, you can change the next hop, you can change the tag, and so on and so forth. So if it matches the SCL, then do this, apply, do this. So generally, that is how a route policy is written. So again, route policies will always be evaluated one after the other, depending on the node ID, like that. So a route will be allowed if it matches a permit clause. Otherwise, it will not be processed. Okay, so let's look at this example. So let's look at this example. So here we're having, let's call it, for example, the routing table of a router, which has several networks. So 2.0/24, 3.0/24, 3.0/25, 5.5/32, 6.6/32. You can also see their cost in this second column here, their cost, and you can also see their next hop. So for example, to go to this network from this router, you can either go through 34.2 or 13.1. So you can use either. We have two equal cost paths. So both of them have been entered into the routing table. So how can we modify this so that we can control our traffic flow, the next hop, the cost, and so on and so forth? So let's look at, let's begin here by looking at the routing policies that we've created here. So we have route policy whose name is RP. Then we are saying deny. So the clause is deny. Then we are saying node 10. So that is the index for this particular route policy. Then we're saying if match IP prefix that has the name pref1. Then after that, we go to another route policy. So we don't have an apply clause. So let's evaluate what is in IP prefix pref1. So we have here the IP prefix. So we will have configured this. So we have the IP prefix here. So IP prefix pref1 index 10 permit. So here we are saying permit 5.5.5.5 32. So what happens? In the IP prefix, we have a permit. In the route policy, we are saying we deny that network. So what do you think will happen eventually? Are we going to learn this network anymore when we implement this route policy? What is your guess? Anyone? So in the prefix, we have permit. In the route policy, we have a deny clause. So are we going to learn this network anymore? Anyone with a guess? I think someone chatted. No. Yeah, true. So unless we have a permit here and permit here, then we can learn about it. Otherwise, it is a no. So this network 5.5.5, it is, we are no longer going to learn about that network. So that is how that route policy is going to be interpreted. So let's look at the next route policy. So same name. This time we have a permit clause, and it's node 20. So we're saying if match IP prefix pref2. So let's look at pref2, IP prefix pref2. So IP prefix, oh, sorry, whoa, I'm sorry. Oh, and we have two pref1s. Oh, I also didn't mention about that. Sorry, I hadn't seen that we have another pref1 here. So we also need to look at this because both of them are going to be looked at, because here we've specified pref1. So let's look at this one too. I had forgotten this one. I'm sorry. This one. So this one also has a permit clause, but now because in the policy we say deny, so this network 2, this one, 1.1.2.0/24 is also not going to be, this one is also no longer going to be learned. So I hope that is clear. I'm very sorry, I had missed that one. So let's go back to this one. We want to look at pref2. The route policy is permitting it. So we now look at it. So IP prefix pref2 index 10. When you give it a different name, you can start from the lowest index. So index 10, then we are denying 6.6.6.6.32. 32 meaning the whole bits must match exactly as it is. So that means that we are no longer going to, because this is a deny, even though this is a permit, it simply means we are no longer going to learn about that network. So it's going to be denied. Okay, let's move on to the next route policy. So this is the next route policy. It has more than one if match. So route policy RP permit node 30. So that's the index. Then we have two if match. So if it matches SCL 2001, then if it matches IP next hop, then so we want to look at SCL 2002, and in particular we are looking at the IP next hop. Then so if it matches that one and that one, we want to apply. We want to change the cost of that network to 21. So let's look at SCL 2001. So SCL 2001 is here. It has a network which is permitting here. So it's permitting 1.1.3.0. So 1.1.3.0, that will match these two networks from that SCL. So remember, you really don't have to look at this. These three parts for the SCL must match. So 1.1.3. So these two networks apply. So I hope that is clear. Okay, then we look at SEL 2002. So we're also looking at SEL 2002. And what does it say? Rule 0, permit source. So we are permitting a source that has this exact address. So 13.13.13.1. And here you see we are saying if match. So if the source network, if the next hop is 13.13.13.1, so that is exactly what you're saying. If match IP next hop SEL 2002. What does 2002 have? 13.13.13.1 exactly. So that is what you're saying. So for any network that matches SEL 2001 and 2002, we want to apply the cost. So simply saying, we want to change the cost for this next hop, for that network, and for this next hop, for this network. So we are changing the cost from 4087 to 21. And for this one, we are changing the cost from 1. So this one we are changing from 4087 to 21. This one we are changing from 1 to 21. So that is what is happening in this route policy. So I hope that is clear. Okay, then let's look at the last one. Oh, actually it's not the last one. The second last one here. So here we are saying route policy RP permit node 40 if match IP prefix pref3. So if it matches pref3, we want to change the cost to 11. So let's look at IP prefix pref3. It's the last one here. So IP prefix pref3 index 10 permit. So it has a permit. Then we are specifying this network. So because it's /24, the first 3 parts have to match. So for that, we have these two. Have those two. Then we're saying greater equal 25, less equal 25. So that simply means /25, /25. So there we're not going to look at /24. We only want /25, /25. So what we're simply saying is that for /25, apply the cost, change it to 11. Change the cost to 11. So we're simply going to change the cost here from 1 to 11. From 1 to 11. Now, the last one here, route policy RP permit node 50. It's simply the very last one so that we can permit all the others that have not matched any routing policy. Because by default, if you don't match anything, then we simply deny. So the very last route policy has to have a permit clause so that other routes can also be learned. So from this table and from how we've evaluated the route policy, that table is going to be reduced to this. So only these two networks are going to be learned, and for the next hop of 131313, the cost has been changed to 21. The cost has been changed to 21 by this route policy. And also, this route policy here has changed the cost for this /25 to 11. So generally, that is how your router will filter routes using the route policy. Anyone with a question? If you need a clarification, please let me know. Can you hear me? Kimeeleweka? Hello?
Yes.
Is it clear?
Itaeleweka tu.
Okay, sawa. Asante. Kama kuna mtu akona swali anauliza tu. Okay. So, what are we doing here? Route policy configuration. Just the first part of it. Okay. So for the scenario that we wanted, we can implement it this way so that you understand it. So you remember we were saying we don't want marketing department to access the finance and R&D department. Again, we don't want the headquarters to access the R&D department. So how can we implement this particular scenario? So of course, between the routers, we are learning routes using OSPF. So we have to area 0 and area 0. So we simply go into OSPF area 0, then advertise the networks that we are connected to. So we do that. We come to this guy. We'll also advertise this one, this one, this one using the network command. And now for RTA, we don't want to advertise these three networks. We don't want to advertise these three networks into OSPF using the network command. We want to import them. So we go into OSPF 1, then we use the command import route direct. So any network that has not been advertised in OSPF area 1 will be imported as an external route, into OSPF. So these three, 10.1.0, 10.2.0, and 10.3.0, they are going to be imported into OSPF. So with this configuration, everyone can talk to everyone else. Everyone can talk to everyone else. Marketing department can talk to finance, to R&D, to documentation, blah, blah, blah. So how do we configure so that marketing does not get to finance and R&D? So that is the next steps now. Okay, so we can use, in this example, we are using a filter policy on RTC. So what we do, we create an SEL, a basic SEL, to identify packets from, to identify actually this particular network, the finance department network, the 10.1.1.0 network. So rule 5, deny. So we want to deny that. Then we say rule 10, permit source any, so that any other thing can be permitted. Then we go into OSPF process 1 and we type filter policy, then the SEL number 2000, then in the import direction. So import means don't learn. When wanting to learn, when you want to receive this route that matches this SEL, then check the clause. Is it a deny? Is it a deny or a permit? So if it's a deny, then you cannot learn about that network. So that is how we disable the marketing department from accessing the finance department. So in RTC, in the routing table of RTC, we are no longer going to see this network, the 10.1.1.0 network. So that's one way in which we can implement the filter policy to stop RTC from learning about the finance department network. Okay, so let's see in RTA. In RTA here, we are using IP prefix. So we have two IP prefixes with the name AB, index 20 and 10 and 20. So for index 10, we are saying permit that network. So that is 10.1.1.0. We're also saying permit the 3.0, this one, 3.0. So we are simply saying in this IP prefix, we want to permit two networks, this one and this one. Okay, so let's see what we are doing in OSPF. Now, in OSPF1, we use filter policy, then IP prefix, and we specify the name. Then now we say export direct. So what are we saying exactly here? What are we saying? Okay, so what we're simply saying is, if you want to advertise direct routes, then check this IP prefix. Anything that has a permit, you can advertise it. Anything that is not there, simply don't advertise it into OSPF. Don't advertise it into OSPF1. So that way, this network cannot be advertised into OSPF. If it is not advertised into OSPF, then RTC cannot learn about the route to R&D, and the headquarters, RTD, cannot also learn about the route to R&D. Therefore, they cannot be able to access R&D, but they can be able to, but headquarters can be able to access documentation, and they can also be able to access finance department. But marketing cannot access finance department because of this. So sijui kama hiyo explanation iko sawa. Anyone with a question? Anyone with a question? Kimeeleweka? Yeah? Hello? Have you understood?
Yeah.
Okay, asanti. Eric, umeelewa? Masunde? Alan? Okay, sawa. So if we look at the marketing department routing table, RTC is the marketing department. RTD is the headquarters. So we begin with the routing table for RTC. Due to those configurations that we've done, the only external route that RTC is going to learn about is this one, .3, which is for the documentation department. RTD will learn these two external routes. 1.0, which is for 1.0 ilikuwa ya finance department, and 3.0, which is for the documentation department. So you can actually see that configuration has worked, and now we've been able to control reachability. We've been able to control reachability using a filter policy. So you can also use a route policy for that particular purpose. Okay, so let's see what we have here. Traffic filter. So we can also use what we call a traffic filter to let me just try and say this again. So we have the marketing department. So it's the same scenario. Marketing department cannot access finance and R&D. Headquarters cannot access R&D. So let's look. Here we want to use an advanced SEL. We want to use an advanced ACL. In this advanced ACL, we are denying any packets that is coming from this network. Remember, we are configuring RTC. So we are denying any packet that is coming from the 4.0 network and is destined to the 10.1.1 network, which is the finance department. This one. Then we are also denying any packet that is coming from the marketing department and is headed to the R&D, like that. Then the last rule, we permit all the other packets from the marketing department. So after that, we go into this interface G001 and apply a traffic filter. So here we're saying traffic -filter inbound. So any packet coming into this interface, apply ACL 3000. So the ACL will be applied on any traffic that is coming in to that interface. So if it matches a deny rule, that packet will simply be dropped. So this is what we call a traffic filter. This is what we call a traffic filter. Unlike a routing policy, traffic filter does not affect routes that are learned. It simply checks the IP data and makes a decision based on the ACL. So we don't want the headquarters to access R&D, so we can also do this. So this is just an alternative. So we can create an ACL, say that deny anyone that is coming from the headquarters, so 5.0 network, and is going to the R&D 2.0 network. Then after that, you have to go to the particular interface that is connecting the headquarters to that particular network and do traffic filter inbound ACL 3000. So any packets coming into G001 has to be evaluated using this particular ACL. So that is how traffic filters work. Okay, so if we check the routing table for RTC, we're going to see that all the external routes have been learned. So we have the route that is going to the finance department. We have it in our routing table. But from a PC in the marketing department, if we try to ping 10.1.1.1, it is simply going to time out because of the traffic filter that we've just configured in the previous slide. Okay. So now let's look at how to adjust network traffic path. So here we can use what we call routing policy, or we can use what we call a policy-based routing. Very interesting terms here. Routing policy and policy-based routing. They can be confusing. Now, in the network optimization stage, network traffic paths may need to be adjusted. Now, when RTA learns about the route to the headquarters using OSPF, now these routes that are installed in the routing table are going to be the optimal routes based on the cost. Therefore, the next stop for packets from the marketing department, from the finance department to the headquarters in this scenario are always going to be forwarded through RTB, because RTB has better bandwidth. So even though this has a lower bandwidth, it still works. It still works. So we need to balance, because if all the packets are passing through RTD, then this link will remain idle, which is not right. And we can also have congestion on this link. Can have congestion because many packets are passing through that direction. So to avoid that, you need to optimize traffic flows within your network. So we have two solutions to that. You can either use a route policy, or you can use what we call a policy-based routing. Now, you use the route policy to change the protocol attributes to control routing table entries and adjust traffic path. So a route policy can be able to control the routing table entries. So that is what is learned, and their priority and their preferences and things like those. Then you can also use a policy-based routing to control traffic behavior. So before searching the routing table, So actually, as you're going to realize, the biggest difference between a route policy and a policy-based routing is that route policy depends on what has been entered in the routing table. It actually checks the routing table and now modifies a number of attributes in the routing table. But policy-based routing does not forward data based on the routing table, but now based on the conditions that have been specified in that particular policy. Okay, so let's see how that works. So we begin with looking at routing policy. So as we know, packets are forwarded by searching the routing table based on the destination address. What that means is, if a packet comes to the router RTA will check the destination address, then look at its routing table. Do I have that network? So we want to send a packet to the headquarters. RTA receives it, searches through the routing table. Do I have this network? Then after that, it goes ahead and looks at the next hop. So I'm supposed to send it to .2, 1.1.2, which is this interface here on RTB. RTB similarly will look at the routing table. Hey, do I know 10.1.3.0? If I find it in my routing table, then I forward it to the next hop. So that is how packets are actually processed. Now, let's look, for example, let's look at this here. Sorry. Okay. So we can see that this path is better in terms of cost, because cost of one, so total 2. But this one, because of the 5 Mbps, we have a cost of 2, cost of 1, like that. Now, one way in which we can use the routing policy to change the traffic flow is by altering the cost of this particular interface here. We can alter the cost. So we can alter actually the OSPF cost. So we simply go into that interface in RTA, so G0/0/0, because right now it has a cost of 1. But we can go into the interface and specify the OSPF cost. I'm sure you've seen this before. So OSPF cost 2, so that it has the same cost as this one. So that now this path is going to have a cost of 3, and this one also a cost of 3. Yeah. So when we do that and we display the routing table of RTA, we are going to see that now both next hops are added to the routing table. 1.2, which is this one, and also 3.2, which is this one. So you can see that both of them have been added in the routing table. So in RTA, if you want to go to this network, you can either go through this or through this. So that is one way in which we can alter the values or the properties of what is entered in the routing table. So in this case, we've simply altered the cost. Initially, the cost for that path was 3. But now we've changed it, and it's now 4. So both of them now match. 1 + 1 + 1, the last one there. Okay. So what is the limitation of that solution? Let's see. So the traffic path from the marketing department to the headquarters is RTA, RTB to RTD. So RTA, RTB to RTD. The traffic path from the finance department to the headquarters is RTA, RTA, RTC to RTD. So what happens when we want such like a configuration? How can we achieve this configuration? Because in the previous configuration, yes, it will work, but it simply means that we are going to have 50-50. 50% of the packets passed through this, and 50% of the packets pass through this other side. So 50-50. But what if we want? So this method has helped us just a bit. But what if we want to specify that traffic from the marketing department should pass through RTB? Traffic from the finance department should pass through RTC. So as shown in the figure, solution 1, the one that we just did, cannot meet the requirement because packets are forwarded based on the destination address. So it cannot meet the requirements of source address based, destination based, address based, or application layer based forwarding. So that one was just focusing on the destination address. But now, what if we want to do a combination? So in order to achieve that, you need to use policy-based routing. Policy-based routing. So let's look at policy-based routing. So with policy-based routing, the routing is based on the source address. That is, the next hop of traffic from the marketing department is RTB. And the next hop of traffic from the financial department is RTC. So we are going to see with policy-based routing, we can be able to detect the source of the packet on RTA and say that if these packets are coming from the marketing department, forward them to this next hop. If they're coming from the finance department, from this network, 10.1.20, forward it to this next hop. So really, that is what policy-based routing is going to enable us. Now, generally, we have several types of policy-based routing. One of them is called local PBR. Number two, we have what we call an interface policy-based routing. Number three, we have what we call smart policy-based routing. This one applies to packets that are sent by the device. Or instead of sent, can I say originate? Applies to packets that originate from the device. So they originate from the device. For example, ICMP packets, BGP packets, and so on and so forth. So any packet that is originating from the device is what we call a local policy-based routing. Now, this one, interface-based policy-based routing applies, let me call it transit, to transit packets. Packets that are passing through the router. So they have not originated from the router. Now, with this one, with interface policy-based routing, you can specify the next hop. You can specify the next hop of the traffic. You can specify the next hop of that particular traffic. With local based, you can, for example, choose a source. You can choose a source address. For example, when you're doing a ping, sometimes we choose a different source address by using the -A command. So yes, we are pinging through a certain interface, but we choose a different source address by using the -A command. So you can change things like the source address in local policy-based routing. In interface policy-based routing, you can specify the next hop. Then you have the smart policy-based routing. This one selects the optimal path for service traffic based on the link quality. So with smart PBR, to select paths for different services based on the link quality, you configure a smart policy-based routing. In this particular training, we are not going to look at smart BPBR. We are going to configure interface BPPR just shortly. So those are the three types of policy-based routing: local, interface, and smart. So policy-based routing will use it will use an ACL to match traffic. Then it will define the behavior for the traffic. For example, to change the next hop of the packets. So to identify interesting traffic, you use an SCL. Then now you can be able to define how you want that traffic to be processed. So let's look at an example here. So in RTA, remember what we want to implement here is we want to implement that packets from the marketing department go through RTB, packets from the finance department go through RTC. So how do we configure that? So in RTA, we can create an advanced SCL 3000. So we permit packets from the 1.1.1.0, which is packets that are coming from the marketing department, if they are going to the headquarters 3.0 network. So after doing that, we can now use what we call a traffic classifier. So traffic classifier, then we give it a name. Then we use an if match. So if match SCL 3000, then we want to change the behavior. So traffic behavior for the same, use the same name. So we want to redirect IP next hop. So we want the next hop for any packets coming from this network and going to this network. We want to change the next hop to 1.12.1.2, which is the IP address of the interface of RTB. So any packets coming from the marketing department is simply going to be forwarded through RTB. Then after that, we do traffic policy Huawei control 1, classifier Huawei control 1, behavior Huawei control 1. So we create a traffic policy with the name Huawei control 1. We specify the control and the behavior, the classifier and the behavior as Huawei control 1. Then after that, we go into the interface G002. So let's look at where G002 is on RTA. So G002 is here, and it's the one that is interconnecting the marketing department. So we apply that traffic policy that we've just created there. Okay, so we now apply on G002 the traffic policy Huawei control 1 on the inbound direction. So inbound is traffic that is coming into this interface. So that is how we redirect packets to RTB that are coming from the marketing department. So similarly, we can do the same for packets that are coming from the other departments, which is the finance department, so that they are redirected to RTC. So RTC is on the next hop for RTC is 13.1.30, maybe .3 or something. Okay. So again, we create an advanced SCL. We use a different number. We permit packets that are coming from that department and going to the headquarters, from finance to headquarters. We create a traffic classifier if it matches that SCL behavior. So again, we want to redirect to the next hop of RTC. Then after that, we create the policy. We specify the classifier and the behavior. Then we go to the interface that is connecting the finance department to RTA, and we apply that traffic policy in the inbound direction. So that's how we do that. Okay. What do we have here? Now, as we said, with policy-based routing, you are not really affecting. You're not really affecting the entry. You're not affecting the entry in the routing table. What that means is packets that match a policy-based route will simply be forwarded using that particular policy rather than using the routing table. So if you go to the routing table and you look at the destination network which goes to the headquarters, the 3.0 network, you're still going to see that we've not changed. We have not changed the next hop. The next hop is still pointing to the 1.1.2, which is to RTB. But now, because we've done the policy-based route, if you do Trasat from marketing department, you're going to see that it's going to pass through RTB. If you do a Trasat from the finance department, you're going to see that that packet is going to pass through RTC. And so 3.2. So when we apply policy-based routing, it does not affect the entry in the routing table, unlike routing policy. Remember the routing policy where we changed the cost, but here everything in the routing table remains the same, but we are simply not going to forward those packets based on the routing table, but based on this routing policy, policy-based route that we've created. Okay. So differences. Some of these things are actually quite confusing, but with time you will understand them better. So routing policy and policy-based routing. So what's the difference? What is the difference between routing policy and policy-based routing? So one of them is routing policy is based on the control plane. So you know we have the control plane and the forwarding plane. So it affects the routing entries. The control plane is where the calculation is done by the protocol, so that it can find the optimal route to be installed in the routing table. So that's the control plane. So routing policy operates on the control plane. On the other hand, policy-based routing actually operates on the forwarding plane. So it does not affect routing entries. Packets are forwarded based on the policy first. And then based on the routing table. That means if the packet does not match the policy, then it is forwarded using the routing table. Actually, but if it matches the policy, we simply send you to the next hop that has been specified in the policy. Okay, routing policy. Policy is based on the destination address. So we saw how that is done, while policy-based routing is based on the source address, the destination address, the protocol type. So you can specify many things, including the packet size, to change the next stop. This one used with routing protocols because it operates on the control plane. So that's why we had to go into OSPF1 and change. We had to go to the interface and change the OSPF cost. So it's used together with the routing protocol. A routing policy needs to be manually configured, hop by hop. So with policy-based routing, you have to configure how the packet will move from one router to another up to the end. So hop by hop. So tools that we used for routing policy include route policy and filter policy. Like in this example, I think we used the filter policy. Here you can use a traffic filter, traffic policy, or policy based routes, etc., etc. So what are the problems caused by route importing and solutions? Let me try and remember. So in the previous example, 4 routers run the same protocol. So what if they run different protocols? What will happen? What if they run different protocols? What will happen? So what they're saying here is we're having OSPF running between those routers and having RIP running between these routers. So what problem can occur if we are having routers in the same routing domain running different protocols? So let's look at number one. Where's number one? So of course, in the configuration, for these departments to be able to talk to the headquarters, we have to import. So import route RIP. So we are importing RIP to OSPF. So that's the first thing we're doing. So we import RIP into OSPF. Number two, again in RTC. So we have to import in RTB and RTC on the boundary routers. So again in RTC, we are importing routes from RIP into OSPF. Okay. Number three, what do we have here? Okay, so number three here, remember the 3.0 network is this network here that is connecting the headquarters. So from these particular calculations of OSPF, the packets are going to be forwarded along this path to the destination. And now this network has been imported, so it's an external network. That's why it has a preference of 150 and the cost is still 3, like what we've been seeing before. But on number 4 here, we also have a route to the same destination, the headquarters, with a preference of 150 and a cost of 4. Maybe that is the one that can follow this path, because this one has a lower bandwidth. That's why it's a higher cost. So number 5, so the problem is still the same. The link is idle. So this route is not going to be installed in the routing table. So this route is going to be idle. The link is idle, low link use efficiency. So what is the solution? So solution is change the OSPF cost on the interface to implement load balancing. So like we did the other time, we can change the cost here so that this cost here is higher, so that both these routes have a cost of 4. Both of them have a cost of 4. So that's one thing we can do. But if we do that again, let's look. So okay. So this is just what I've already explained. This is what I've explained on the suboptimal route. So the problem is when you import this destination from RIP to ISIS or to OSPF. If you import them, only one route is going to be installed in the routing table based on the cost. So the one that has a higher cost is going to remain idle. So no one is going to use this link because of the cost issue that I've just explained. So one of the solutions you can do is to use, you can filter routes So let's see how we're doing that. So we come here on ISIS1, we import route RIP1. So we want to import RIP routes into ISIS, which will also import this particular network. Now on RTB, we can do an SCL 2000/2001, then rule 5 deny source 2.0.0.0, and that particular inverse mask. Then the last one is the permit there. Then we go into ISIS1 and we say filter policy 2001 import. So we are simply saying that RTB should not learn about this network. Import. Let me just see here. A display IP routing table. Okay. Good. So we can see here that in the routing table,